Well, ladies and gentlemen, I think we should start this session. Today's keynote speaker is Professor George Fox from the University of Wisconsin, Madison. For the conference, I thought that the duty of the chairman would be to sketch a portrait of the speaker. But to my great delight, I realized that the organizers actually did it for me last night. So what remains is just to indicate the title of the talk, which is Some Aspects of Statistical Design in Quality Improvement.
I used to think that quality control, as it was called, was a very boring subject, and I think it was. But I think what is happening now is something that's rather different and that has certainly economic consequences that are very important and social consequences that are very important, as well as research consequences which are important. So I thought I would say something about those other aspects, as well as perhaps indicating a couple of research problems that come up. First of all, on the economic aspects, Professor Wheelwright of Harvard is fond of putting up that list of things, automobiles, cameras, stereo components, and so on, and he asks the question, what do they have in common? And the answer is that during the last 10 years, the United States has lost at least 50% of its market to foreign competition in every one of those articles. Another interesting, this was a graph which was put up by Mr. Bakken, who is a vice president of the Ford Motor Company. What it shows is the number of times a car is returned in the first 6 months of its life. These are careful records that are kept in the United States for General Motors, Ford, Chrysler, and European cars. And this covered a period of about 10 years. And you can see that things were not getting much worse, and they weren't getting any better, and they were just about on a level. But during this period, the Japanese cars were doing that. So what is it that they're up to? And what is it that maybe we should be up to? And of course, a major reason for high quality and low cost is use of statistical methods and the use of scientific method in general, and a sort of democratization of simple science. Well, scientific method to do what? To learn about the product and the process. So I think in order to understand this, one has to ask some rather basic questions, like, well, what do we mean by scientific process? How do we find things out? How did we discover how to make fire? And how did we discover how to make champagne? Well, it's said that 200 or 300 years ago, I think a French monk happened to notice that in wine there is a second fermentation, which, if properly encouraged, would give rise to champagne. Now, wine has been made for several thousand years, and yet it wasn't until quite recently that that was discovered by that monk, God bless him. And you can see, in order for that discovery to be made, two things had to happen. A critical event, which was the second fermentation of the wine, and a perceptive observer, who was the monk. So this is what we need then for human beings to find things out. Critical events, unfortunately, are rare, and perceptive observers are also rare. And so what we are looking for is the coincidence of two unlikely events, and so it's not surprising that in the 13th and 14th centuries and so on, when all this was allowed to happen by chance, that they happened rather slowly. It was true that if you looked at ships in the 14th century, they were a little better designed than ships in the 13th century, but not all that much. I was looking at the Vasa ship in Stockholm, and there were troubles with that. It capsized on its first voyage. That was in 1630. Well, scientific method came to start to be used 300 years ago or so, and this resulted in a tremendous increase in technological change, which was brought about by, I think, by thinking, well, partially anyway, by the two following ideas. If it's true that you have to have a critical event and a perceptive observer, then you should make sure that naturally occurring informative events are brought to the attention of perceptive observers. So this is one way to encourage the speeding up of that process. The other is to induce the occurrence of informative events. I'm going to call this informed observation and this directed experimentation. An example of the first would be a quality control chart. We are saying a naturally occurring possibly informative events. And we have to be alert when something which is possibly informative occurs, and we have to have somebody there. We have to make a chart, not bury it in the computer or fail to record it. Someone there who can say what happened there. Joe spat in the batch. Okay. If Joe spat in the batch, then let's make it so that in future Joe cannot spat in the batch. Let's build a screen or do something. Directed experimentation increases the probability of informative event occurring. I'm not a very good artist. This is Benjamin Franklin. An experiment is an invitation for an informative event to occur, and you can see that Benjamin Franklin is flying his kite and showing that the emanation that's coming from the thundercloud is in fact the same as the emanation which can be produced in the laboratory and is called electricity. Now, when you think about these ways of speeding up learning, one thing one has to remember is that one can have very fancy techniques, but I suppose on some sort of scale the effectiveness and the fanciness must go through a graph, which is something like that. That as you get more and more fancy with what you do, the effectiveness probably falls off and becomes reaches some sort of asymptote. The number of people who can actually manage to do fancy things, of course, is limited. So that if you're going to talk about any sort of quality revolution where all the people are going to be involved in, which we are talking about, everybody in the company, from top to bottom, is working in this, then you have to get the idea that if this is the distribution of technical sophistication in the workforce, then some of the methods that are going to be used are going to be rather simple, but that doesn't necessarily mean that methods which are fairly simple couldn't, and could be used by a very large number of people, couldn't be quite effective. So let's talk then about this first thing that I mentioned, which is just observing what happens and seeing how we can informed observation. The idea is that every process generates information that can be used to improve it. And what do I mean by a process? Well, the natural thing you think of is a manufacturing process. But the interesting thing about this is we're not really talking just about manufacturing. We're talking about drafting, invoicing, computer service, about how you get into a hospital, for example. Sometimes it's rather difficult because of a lot of silly things that people do, because they haven't studied the process of admission to a hospital. And all kinds of things of that sort. Everything we do, in fact, if you try and get a ticket to fly somewhere on Northwest Airlines in the United States, for example, it takes, has been taking an unusually long time, and also you may not get where you're going on Northwest Airlines, or where you intend to go. So this process, I want to point this out before I mention the fancy bits, is something that, what we're talking about here is something really rather simple. And some of the techniques that are used are very, very simple techniques. Ishikawa in Japan has a particular classification. He talks about the 7 tools in his guide to quality control: Pareto charts, cause effect diagrams, check sheets, histograms, and so on. And just to give an idea of the sort of thing he's talking about, these are techniques that are used by the workforce, not by the people with higher degrees and so forth. He's talking about this sort of thing, a Pareto chart. What is it? Well, the idea is an idea of Durand's. People are making, let's say, springs, and during the last week, they've produced 237 springs which were thrown out. There's a heap of them over there. You don't just throw them out, you count them, and you say, how many did we throw out because they had cracks, how many because they had scratches, how many because they had pinholes, and so on. And you say, well, look, chaps, we threw out most of them, 185 of them, because they had cracks. So let's work on the cracks first. And even though the boss over there, who never comes and looks at the process anyway, says, I know the thing is all caused by pinholes, you say, show me the data, show me the data. And you don't look at the pinholes, you look at the cracks. And then you say, okay, cracks, let's all gather round, get the people who make the thing gathered round and say, we've got too many cracks. And you say, what causes cracks? And they say, I think that the inspectors are inspecting for cracks, and there aren't any cracks there. It's just the inspectors are just imagining the cracks. Somebody else says it's in the assembly. Somebody else says it's in the hardening process. Somebody says that springs of type A have many more cracks than type B. I wonder why that is. Well, you can argue about these things. It's an opportunity to get all the questions raised and to know what sort of data should be being looked for. A histogram is a simple diagram, of course, but it becomes very much more interesting when it's split. And for example, you could take the histogram and split it into 2 bits, one for type A and one for type B cracks. And you could say, well, it's obvious that we're getting more type A's and type B's. What's different between type A and type B? And in following this kind of detective trail, which is what we're involved in, instead of being a policeman, the quality man is now a detective, and people are being invited to become amateur detectives, which is a nice thing to be. So the benefits of this are improved product and process, improved morale by the workforce, managers have time to manage. Well, will it work outside Japan? My late colleague, Bill Hunter, 2 years ago, taught a course at Madison on quality, and he had us all go to see a plant just outside Chicago, which is now run by Panasonic, where they make quasar television sets. And it used to be run by Motorola, which is an American company, and it's been written up in the literature. We went to see it, and we were shown round. They told us that when they took over, the defect rate on the production line for making television sets was 146%. Now you may wonder how you get 146% defects. It's quite simple, actually. It means that most television sets were being taken off at least once, and some television sets were being taken off twice off the line as they came around. By using these very simple techniques, over a period of 4 or 5 years, they got this down to 2%. And this particular picture was up on the wall, 25 foot high, so everyone could see it. And this was all being done by native Chicagoans. There wasn't a Japanese in sight. There were no Japanese managers, there were no Japanese workers. They were the same people who'd worked there when Motorola ran it. So I think this is something that's very important. The old idea was inspect bad quality out with quality control charts and pass-fail inspection schemes. The new idea is don't rely on those things, build good quality in and keep working at it. Now you can see that, and this is where the story really starts, you can see that you can play around with this 7 tools, improving the process and so on, maybe improving the product. but it's complete. I mean, suppose the process and the product are badly designed to begin with. It's just a rotten process. Then all the polishing you can do with this kind of stuff is you can only make it. You can make whatever you can out of a sow's ear, so to speak, but you can't make a very good process out of a bad process to begin with. And so this brings in the business about getting in and having a good process and a good product to begin with. And this is where experimental design becomes important. And I should mention Dr. Deming, because he's the sort of grandfather and the prophet of all quality in the United States. He has 14 points. What his 14 points do is to get management to actually try to do this, because without management support, you can't do it. So let me then get on to say, I mentioned there were some research problems which come up, and there are in both these areas. I'm going to say something about experimentation and about using fractional factorial designs. Now, fractional factorial designs have been around for a very long time. Fractional factorials and other orthogonal arrays. Early development. The first fractional factorial design to be used in industry was run by Tippett in 1933. Then he developed the basic, some of the basic theory. Plackett and Berman introduced orthogonal arrays which weren't fractional factorials, and so did Dr. Rao, developing this still further in 1947. And these designs have most recently been used in Japan to ensure better designs of product and process. Now, they work quite well for purposes of screening, and some of us have known this for a very long time, of course. And the question is, why do fractional factorials work quite well, very often, in a screening situation? Well, possible rationales are the symmetric filling of an experimental space. Another rationale is that you claim that you know which are the important interactions, and so you can sort of design the experiment around these interactions and just estimate the ones that are important. And the third one is the use of the projective properties of designs in expectation of a Pareto effect. Now, I don't think that this, well, there may be some truth in this. This rationale I don't really go for these days very much, because it seems to be saying here that we don't know what the first order effects of the, we don't know which factors are going to have first order effects, but we can know by some way of taking thought which are going to have second order effects in two-factor interactions. So this doesn't seem to me to make any sense, this second rationale. I mean, there may be cases where engineers can say, I expect these things to interact, but if they know all that much about it, they can re-parameterize the problem, so in the new parameterization they won't. So I don't like that. This one, I think, is the important one. And the idea here is really, this is an oversimplified picture, of course, but the idea of the projective rationale is to say, well, suppose, for example, you run some kind of fraction, then in a lower dimension, a lower dimensional space, you can have complete factorials or complete factorials replicated in every possible selection in lower dimensions. For example, here's a set of pluses and minus signs for two-level, could be two-level design, and actually it is a 2 to the 4th factorial if you use this column, this column, this column, and this column. Or it is a half fraction, a 2 to the 5 minus 1 resolution 5 design if you use, or if you like, a strength 4 if you use these 5 columns. And it's a 2 to the 8 minus 4 resolution 4 design, strength 3 if you use those 8 columns, and so on. So as you can use this design in various ways. And so the design gives you one replicate for 2 to the 4th in every one of the 5 projections in 4 space. It gives you 2 replicates of a 2 cubed in every one of the 56 projections in 3 space, and so on. So that if you had a situation where you believed in a Pareto effect, you believed that only a few of these factors were going to have important effects, and supposing you said not more than 3, then you can say, well, if I run this particular design with 8 factors, whichever of the 3 turn out to be important, I've got them covered, so to speak, with a complete 2-cubed design in those 3 replicated twice. Well, so let me just say then a couple of ideas which we've been looking at. We have now a Centre for Quality and Productivity at Madison, and one of the things we've been doing is doing research in some of these matters, and there are about 23 research reports have been published on various aspects already from the centre, and this is a reporting on just a couple of things which came up. Now, really, what we're looking for here is not in these things I'm going to be talking about. We're not really doing anything very fancy. We're really trying to identify the model in the sense of the word, the way it's used in Box-Jenkins, for example. We are saying, let's try to give a preliminary look to see what's happening here. If we want to be fancy afterwards, when we think we know what the model might be, then we can always fit it in a more, use maximum likelihood or something like that to fit it. But in the preliminary stage, we don't know what model we should be looking at. So we're involved in a sort of identification. And the first thing I want to talk about is the business of one of the things that's very important these days, and it's emphasized a great deal, is the use of experimental design, not just to adjust location to increase the mean, say the mean response, the efficiency of the process or whatever, but also to reduce variation. And you can see that in a general way, you can imagine a process being run under different sets of conditions, and you can imagine, for example, this is a very simple example, just 3 variables, and you can imagine that under these different conditions, there might be changes in mean, there might be changes in variance, and might be changes in lots of other things as well. And you might be measuring any one of those things that seemed of interest from the quality point of view. Well, certainly minimizing some measure of dispersion is very important. And if you analyze that particular set of data, for example, you'd find that temperature is the thing that's affecting the mean, mostly. As you change there, you get a change in the mean. So if you want to change the mean, adjust the mean, you should be using temperature, not the rate and the pH. And if you, it's the pH which is affecting the variability. Those are the variances. You can probably see the variances on the back face are much less than they are on the front. So you can see that questions come up about looking simultaneously at the mean and the variance, because you'd like to have a process which is adjusted to be the right mean with the smallest possible variance, and you'd like to use experimental design to do that. Now the problem is that if several repeat runs have to be made at each point, then the size of the experiment may be prohibitive. And so a question arises, and a question which I worked on with Dan Meyer, was to what extent can we find out something about dispersion effects from fractional designs? Well, here is an experiment. It's 9 variables in 16-run experiment, and it's an experiment on welding, which is in the book by Dr. Genichi Taguchi, a Japanese statistician and engineer. And it's, again, this same array in which variable A, which is the kind of welding rod, is this column, and variable B, which is the period of drying, is this column, and so on. Anyway, if you look at the results on the tensile strength, so you're varying 9 factors which affect the welding process. You look at the tensile strength. The way I think many people would analyze this, and first go around anyway, would be by just plotting the effects on normal probability paper. If you do that, you seem to have it's plausible. This is noise, and that you have two factors here which are important, which are standing off from the normal plot, which is the drying method and the material. So you might say, well, it looks there as if this Pareto business has come roaring through, that you've got a couple of factors, drying method and material, which are the important factors, and the other ones are probably mostly in for the ride. But if you then say, well, if that's true, let's suppose that's true for a minute, then one thing we might do is to say, so if we project that design, that 16-run design, into those two dimensions, B and C, and then we've got it's like a 2 to the 4th, a 2 squared factorial in those two variables, repeated 4 times over. So if you look at the data from that point of view, you see a picture that looks like that. So here's the material, and here's the drying period. And you can see the variation here. I mean, you can see, first of all, the mean is changing in the way that the factors said it would. As the drying period is increased, you get a change in increase in tensile. And going from material A to material B, you get a reduction in tensile. But what you notice here is that there's very, very much more variation when you're using this material when you're using that material. And now, there are various explanations, there would be plausible explanations of that. You could say, for example, well, maybe the other factors only affect the material, only affect the weld when we're using this material. That's a possible explanation. So these are, in fact, due to the other factor. If you do an analysis on that basis, you don't find anything very clear in that way. There isn't one factor or two factors that seem to be accounting for that. So what it may well be is that you do, in fact, what you have done there is to detect a dispersion effect. In fact, you've not only found that it may be that you've not only found that material C, that C and B affect the mean, but also that C affects the variance. So let's look into that a bit, because it's rather surprising when you think about it, because you can say, well, we've already, I mean, here we are with a tremendous fraction. I mean, it's 9 factors we're running with only 16 runs, so we should be, if it's a full factorial, we're running 2 to the 9th, we're only running 2 to the 4, so it's a 1/32 fraction, and so we have all these aliases which are there in the mean, so to speak. But now we're saying, in addition to that, we're going to start looking at variances. And so, where can all this be coming from? You know, we've only got 15 comparisons we can make. So, I mean, obviously, one thing which is going to happen is that you're now going to get aliasing from dispersion effects. Dispersion effects are going to pick up in some way. There's going to be some kind of aliasing between location and dispersion effects. Well, let's define a dispersion effect as with a location effect, it's just the mean of the observations at the plus level compared with the mean of the observations at the minus level. So let's similarly define the dispersion effect as the variance of the observations at the plus and minus level. If you do that, and you look at these dispersion effects, you don't get the right answer, which you wouldn't expect to get, really. But anyway, you don't get the right answer. You get factor D coming out as being the factor which produces the large effect, and not factor C. And the reason for that is because of aliasing. The way these aliases go is this. I can write down a formula for it, but what I'll do is simply show you an example. They all look like this. Suppose you take the variance at the high level of D, factor D, and compare it with the variance at the low level of factor D. Then you can show that you can rewrite those expressions for the variances in terms of the differences between the location effects, in other words, the ordinary effects. And if you note the location effects by 2 hat, 3 hat, 4 hat, and so on, meaning the location effect associated with column 2, the location effect compared with column 3, and so on, then what you get is a set of different squared differences that look like that. So this shows how the dispersion effects are related to the column effects. In fact, they're aliased with the column effects. Now, what is happening here, the reason that you don't get the right answer from B is because this 14 is carrying factor B, column 14 is carrying factor B, column 15 is carrying factor C. And so you're getting a B minus C. Those are the two big effects. And so you're getting a difference of those two big effects, which numerically aren't very different, and a sum, one in the numerator, one in the denominator. And that, of course, is completely messing up this comparison. Now, the way you can get rid of that, of course, and the way you'd expect to get rid of it, is to simply take the variances after you've taken out the effects of the taken out the location effects. And if you do that, in other words, you take residuals and you analyze from that. There are other ways of doing this, and some of that's been looked at by Vijay Nair and Dave Pragabon and other people. This is one way to do it. If once you've decided on an identification, then you can estimate the location and dispersion effects simultaneously. One way to do it is using an iteration, which was originally due to these authors. So I think this is an interesting thing to remember, that you may be able to identify dispersion effects from fractional designs. Now, I hasten to say, people get very confused about what statistics is about. And one of the things that's confused everybody is this business about decision theory, and that statistics is based in, it is all about making decisions and so on. I suppose it is in a sense, but ultimately. But remember that I'm talking about an iterative process, an investigation that's going on, a long-term investigation where a series of experiments are going to be done. And what we're looking for there is we're not saying let's do a one-shot experiment and then we stand back and draw our conclusions and we're either hung or congratulated with the results of that thing. We're not doing that. We're carrying out an investigation and we're trying to get clues. And we're saying, what's the next thing we should be looking at? What's worthwhile doing? And what this is saying is not we have proved that there is a B, a C location effect and that there is a C dispersion effect. We're saying that it looks as though there might be, and we've got that conclusion, or we've got that suggestion very cheaply, and now we can carry on at the next stage, and one of the things we'll be doing at the next stage is checking it to make sure that's right. Okay? And running an experiment where we can concentrate attention on that. Another thing I want to talk about is a way of analysing fractional factorial gains, again with work done with Dan Meyer. There's a problem in analysing any kind of fractional design because in an unreplicated fraction, and very often we're working in this area with, we can't use large numbers of experiments. We've got to try to economise all the time on experimentation. And so before 1959, when these designs were used, people used to pool, I think, in the analysis of variance and feel rather guilty about it, pooling the small mean squares and so on. But Cuthbert Daniel relieved us of our sense of guilt by introducing normal plotting methods. And what we've tried to do in this thing that I'm talking about now is we've tried to include some of the ideas which are involved in normal plotting a bit more specifically. Here's a fractional design, 8 variables in 16 runs, mold temperature, moisture content, holding pressure, and so on. Here are the estimates of the effects. Here is the here's the plot, the normal plot, and it's showing holding pressure and screw speed, and a possible interaction as being well, holding pressure, a possible interaction, and screw speed as being possibly important, and this booster pressure over here as another possibly important variable. Dan and I put together a Bayesian model. We said any such analysis depends on implicit prior assumptions of effect sparsity, in other words, of a Pareto effect. So what happens if we incorporate those explicitly? Now, again, I'm not saying don't do any normal plots anymore, do this. I'm saying this would be an additional thing you could do, which might be of interest. You let the effects, standardized effects, have a model which looks like this. You say there's a probability 1 minus alpha. Alpha might be some amount like, say, 20%. So they say an 80% probability of what you've got for an effect is purely noise. There's a smaller probability, say 0.2, that what you have is noise plus a real effect. If you put that model together, when you say now the standard deviation of this distribution will be k times the standard deviation of that one. If you then go through some standard algebra, you can get the posterior probability of the tau i's. That's the tau I is an active factor, and you can also get the posterior distribution for sigma, and then you can do this integration numerically, and this can be done with a computer program quite quickly. The only question is to guess what alpha and k ought to be, and we did this by going through the literature and seeing, by looking at past examples of fractional factorials, finding how many factors, when they used fractional factorials, people thought they had. And we said that ought to give some indication. And then by taking the ones that they thought were effective and comparing those with the noise, one could get an idea of what k was. And we ended up with an estimate of about 0.2 for alpha and about 10 for k. And you can see, if you analyze that design that I've just just showed you, you get this kind of thing. The probabilities associated with factor 3 and factor 5 and the 3-8 interaction are very close to 1, that those facts are active. 8 is sort of questionable, and that agrees pretty nicely with the sort of thing getting on the normal plot. Well, what are we going to do about this thing? We don't know alpha and k. We don't know that alpha is really 0.2 and k is 10. What we've done is to simply do a sensitivity analysis and say, well, if we look through the literature, we find that most of the time alpha is between 0.1 and 0.3 anyway, and k is between 5 and 15. And so what we've done is to just let those parameters vary over those ranges and see what happens. What seems to happen is that the factors which are sticking out as being very active don't change the probabilities very much. The one that changes a great deal is this one, 8. But you notice that what this is saying is, it's saying, well, it depends how you look at the data. I mean, if you felt very strongly that there were a lot of effects there, you'd have somewhat more probability if you felt there were less effects there. But it doesn't really change the conclusions very much. It simply says that nothing's going to move this up to there, for example. So it does seem to me this is quite a useful kind of analysis, and we've run this in many examples. I don't have time, I think, to give you a final example, but just let me mention it anyway. There is coming out a 81st birthday volume for Cuthbert Daniel, and one of these days...
Might be 82nd.
Yes, maybe 87, yeah. Thank you. Anyway, one of these days we're going to see this, and there is a paper in there about how you can modify this method to allow for possible faulty observations. Thank you.